this is the outline of my presentation. So today I would like to talk about analog versus digital circuits. What is the difference between analog and digital? Okay, so what is the difference? And I'll talk about the digitization of analog signals. And if I have time, I would like to introduce binary numbers. Okay, next lecture, I'll talk about number systems, number system conversions. So all of these topics will be covered during this week, inshallah. Okay, so let me start first with analog versus digital. Can anyone explain to me what is the difference between analog and digital? Any idea? Anyone?
Analog is infinite.
Okay, and
well,
digital
is limited. It's countable.
Can you be actually more specific what you mean by actually infinite?
It's like analog is real numbers. It can be anything in the range of real numbers. While digital is only integers. You can count it.
Okay, now you are actually more specific. Yeah, good description. Okay. Type. So the way that anyone else would like to have like a definition for analog versus digital?
Analog variable physical and digital it is digital. You can
I can't hear you. Can you raise your voice again? So analog means what?
Variable physical and digital means in computer. We can catch it.
Okay. Okay. So basically, you are saying that analog is something which is physical, whereas digital means that something that you are storing inside a computer, right?
Yes. Yes. Virtual. Yeah.
Okay. Okay. Good. 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 Yeah, you have really a good idea about the difference between these two. Okay. Two important concepts. So, so analog here. Let me just move my mouse. Okay, back here. So analog means continuous. Okay, like someone said, real numbers. Okay, so when we talk about an analog parameter, okay, it can have a continuous range of values. It does not really have to go to infinity, but continuous. Okay, it means continuous. Okay, so for example, temperature is considered to be an analog parameter. So the temperature, it increases and decreases continuously. Okay, so that's actually, you can think about analog, you can think about temperature as an analog parameter. It's like a continuous mathematical function. Yani, for example, if the temperature outside now is 40 degrees and it wants to go up to 41 degrees, it's going to go continuously. It does not really jump from 40 to 41 suddenly. It goes from 40 to 41 continuously, right? So you have actually a continuous range of values between 40 degrees centigrade and 41 degrees centigrade. Okay, so that's temperature, which is an example about an analog parameter. You need, of course, a temperature sensor, okay, to sense the temperature. Do you have other examples about something which is analog? Any other example?
Maybe velocity or speed.
Yes. So if you are measuring, let us say, the speed of a car or the speed of anything, of any object, yes, so that will be, for example, something which is called an analog parameter. Yes, excellent.
Time it takes something to do something.
Something about, can you be
Time.
specific?
Time. Measuring time for something.
You mean time? Time,
Yes.
time. Time itself, yes, is continuous. Yes, time itself is continuous. And you can think about time as an analog parameter. Okay, good. On the other hand, we have digital. It means digits. It comes actually from digits, so numerical digits. So you have a fixed set of discrete values. For example, the number of a month, okay, it can be from 1 to 12. You can have a month number to be either 1, 2, 3, and so on, up to 12, but you cannot really have the month number to be, let us say, 1.5. 1.5 is not a month number, right? It is either 1 or 2, but not 1.5. So you can think about the month number as a discrete value, as it can be represented by a digit. So we call it actually a digital parameter. We call it a digital parameter. Do you have other examples? Other examples about a digital parameter other than the month number? I just gave one example here. Give me another example about something which is like a digital parameter. I cannot hear anyone.
The charge of the battery of a phone or a tablet or any device.
The charge. Okay, but really it's representing it in digits, but really the charge is increasing continuously, right? So when you are charging a battery, the charge is increasing continuously over time, but it's showing it as digits. Okay, but so we cannot consider this really as a digital parameter.
I have an example. The number of absent I have in this course.
Okay. Okay, good. Okay, so that actually can be considered to be something which is a digital parameter. Or you can say the number of days, okay, the number of days in a week, or the number of days in a year, okay, that actually can be counted as a digital parameter. Okay, good. So now we understand the difference between analog and digital, okay? So analog means continuous, digital means that you can represent it with numerical digits. Good. Now, do you think computers are analog or digital systems? Are computers analog or digital systems? What do you say?
Digital?
Yes, of course, digital. Everything is represented inside a computer system. It's represented with digits. Yes, it is actually a digital system. So computers are digital systems. So do you think that which is easier to design, an analog system or a digital system? Which one is easier?
Digital.
Digital, yes, of course. Digital systems are a lot easier to design, okay, because they deal with a limited set of values rather than an infinitely large range of continuous values. So for this reason, digital systems are easier to design. Now, the world around us is analog. Okay, so I talked about temperature. You can talk about speed, acceleration. All of these are analog parameters. So it's common to convert these analog parameters into digital form. Sound, for example, is an analog form. Okay, it's an analog so sound itself is analog. But what you can do is that you can digitize, okay, the sound, and you can store it as digits inside a computer system. So this process of converting an analog signal into a digital signal is called digitization. Okay. So this is an example of digitization of analog signals. So you want to convert an analog signal into a digital form. So the analog signal is a continuous signal. Okay, it's like a continuous function in mathematics. Okay, so here's an example of an analog signal, and we are representing it as a function. And you can see that we are representing time and the voltage. So time here is the x-axis and the voltage is the y-axis. And you can see that how the signal is going up and down over time. Now, if you want to digitize, okay, the analog signal, you need to represent it with specific voltage values. So you can choose specific voltage values like V1, V2, V3, and V4. These are only 4 voltage values. And now you have to decide, okay, what's the value of the signal at a given point in time? This is shown in the next slide. So you can see the analog signal, and at each point in time, we have to decide whether the value is V1, V2, V3, and V4. Now, this is an electric signal, okay? So here it's represented with a voltage electrically, okay? We don't really care about these values, V1, V2, V3, V4. All what we are caring about is that, okay, there are only 4 possible values. So when we digitize an analog signal, we assign, okay, a value, okay, to the signal. So after actually digitizing it, it becomes as shown below. Okay, so now we have converted the analog signal into a digital signal. So it can be V1, V2, V3, and V4, but nothing in between. Nothing in between. Only these 4 possible voltage values. Now, which one do you think is more accurate? Is the analog signal is more accurate or the digital one?
The analog.
The analog, yes, because it can represent all values between V1 and V2, and all values between V2 and V3, and between V3 and V4. All of these values can be represented. And if the voltage goes above V4, it can be represented with the analog signal, but it cannot be represented with the digital signal. So the digital signal can only represent only 4 possible values. So now there is a loss of accuracy. Okay, so once we have converted the analog signal into digital form, we have lost accuracy, right? So how to improve the accuracy of the digital signal?
We can increase the range of voltages.
Yes, so we can actually add more voltage values. So between V1 and V2, we can introduce more. Between V2 and V3, we can introduce more. So therefore, we can actually add more voltage values. So rather than having only 4, we can have 8, we can have 16. We can even have more, right? So the more voltage values we have, the more accurate, okay, the digital signal will become. That's really the idea, okay, to improve the accuracy of the digital signal. Is this clear? Do you have any question about this?
Doctor, when you say add more values, do you mean add more values between the already existing 4 values?
So right now we only have V1, V2, V3, V4, right? Now between V1 and V2, I can actually add another voltage level. I can actually add another voltage value. So I can actually have, okay, between V1 and V2, I can actually have, let us say, a voltage value in between, and this will make it actually more accurate if you have the voltage around this value. The same thing between V2 and V3, the same thing between V3 and V4. So rather than representing, okay, the voltage with only 4 possible values, so you think about V1 to V4 as 4 possible digits, okay, 4 possible digits. And we are storing this digital signal using only 4 possible values from 1 to 4. If you double them, if you make them from 1 to 8, okay, then basically these voltage values will be closer to each other, and the digital signal will become more accurate and very close to the analog signal. The more voltage values that you add, okay, so these voltage values will be stored inside the computer system as digits, and therefore the more accurate the digital signal, it will become more accurate.
Yeah, but
Okay?
you will still distribute them over correct numbers, right?
So exactly. So now you can actually have something between V1 and V2. So V2 actually can be closer to V1, and V3 can be closer, and so on. And so we can actually have V5, V6, V7, V8. Okay. So basically, we can actually have these voltage levels closer to each other, and therefore we can actually have a more correct, okay, or more accurate,
precise number,
more accurate representation, yes, of the digital signal. Oh, so now the world around us is analog. So, for example, look at sound. Do you think that sound is analog or digital? Is sound analog or digital?
Analog.
Analog, yes. So basically sound is like vibrations, right? So when you have the sound waves, the sound wave is going to vibrate, okay, the air, okay, the air molecules, okay, and then it's going to reach your ear and enter your ear. And then once it actually enters your ear, the brain is going to interpret this sound. So I'm talking now to you, right? So basically the sound is coming out from your speaker into your ear, and the brain is trying to interpret, okay, the meaning of this sound, okay? It's converting the sound pattern into some kind of a meaning. So the sound itself is analog. So now I'm talking actually to you, right? So my input here is the sound, which is an analog signal. Now the sound is going into my microphone. Okay, so the microphone is acting as an analog to digital converter. So this analog to digital converter is very important because it will convert the analog signal into a digital form. Okay, so you can see here on top, okay, I have here the analog to digital converter. So think about sound here, okay, as my input. So the microphone here is acting as an analog to digital converter. So it's taking the sound and converting it into a digital signal and storing this sound. You can actually store this sound, okay, as digits. So you can actually have a sound file and you can actually store them as digits inside your computer system. Okay. Now, in my case, okay, the sound will be what will happen to actually to the digital signal. So once the analog digital converter has converted this sound, so now the sound is a digital signal. So basically, it can be stored as a sound file inside the digital system on a computer system, for example, or it can be transmitted through a network as a digital signal. Now, over the network, okay, your computer system is receiving my sound as a digital signal. You can actually store it. It can be processed. Your computer system is a digital system. Okay, so you can actually store it. You can actually do anything to the sound file that you are storing. Okay, you can process the sound if you want to. But then you can actually here receive it, okay, on your computer system as a digital signal. And once it is received on your computer as a digital signal, your speaker is acting as a digital to analog converter. So it's converting the sound from its digital form back to the analog, so that the speaker is actually again transmitting the sound, okay, to your ear so that you can understand what I'm saying. Okay, is this clear? So you can see that the world around us is analog. I just mentioned the example of sound as an analog signal. So we need analog to digital converters, okay, to convert the analog input into digital signal. Now, this digital signal can be stored or it can be processed by a digital system, like a computer system. Okay, so the computer system is a digital system. And now when you would like actually to, let us say, to transmit the digital, let us say, sound over a network and receive it on another computer system. So once it has been received and you would like to hear the sound, there is another converter that will convert the digital signal, the digital sound, back to analog. So it will output, so the input to the digital to analog converter is a digital signal, and the output will be the analog signal. For example, the speaker that you have on your computer system is a digital to analog converter, okay? And once it outputs the analog signal, the sound wave is going to reach your ear and you will understand what I'm saying. Is this clear?
Yes.
Do you understand this?
Clear.
You understand this?
Yeah.
Okay.
Yes.
So the way that the sound is stored on your computer system, it's stored in a digital form. However, the sound itself is an analog signal. So therefore, it has to be converted from analog to digital in order to save it in a file, okay, as a digital sound on your computer system. And later, if you would like actually to play this sound file, or you would like to hear it, there is another converter that will convert the digital signal back to analog. So this is called digital to analog converter, which is shown at the bottom, okay, that will output, okay, the sound, okay, back into its analog form. So it becomes a sound wave, and therefore you can actually hear it, okay? Now, our focus in this course will be on the digital system, which is shown in the middle here, which is shown in yellow, okay? That's our focus in this course. So everything, so all the input to the digital system will be a digital signal in digital form, and all the output will also be a digital signal in digital form. So our focus in this course is called Digital Logic Design. That's the title of our course. So we are dealing only with digital input and digital output. We are not dealing with analog. Okay, so electrical engineers, they deal more, they have two types of circuits. They have digital circuits and they have analog circuits. In our case, our focus will be on digital circuits and digital systems. We are not dealing here with analog, okay, circuits or analog signals. Okay. So we understand the scope of this course. So everything that we are talking about in this course, we are talking about digital systems and digital logic design. Okay. Any questions about this?
Everything is clear.
I still actually have only a few minutes, 5 more minutes. Right. Let me talk about binary, okay, numbers. Now, how do computers represent digits? So as I said, a computer system is a digital system. So everything which is stored inside a computer system, it's stored as digits. I mentioned the example of sound. So the sound itself is converted from analog into digits and stored as digits inside the computer system. The same thing for images, the same thing for video. Everything is stored inside the computer system as digits. But how do computer systems represent digits? Any idea?
Zeros and one?
Exactly, in binary. So we only need 2 digits. Now, we human beings, we use 10 digits from 0 to 9. We are used to the decimal number system. Okay.
A combination of zeros and ones that represents the.
We can actually represent anything. We only need 2 digits, only 2 digits. So we call them actually binary digits. So binary means 2, okay? So binary digits, we only have 2 digits, okay, 0 and 1. These are the simplest to represent inside a computer system. So for example, you can use an electric voltage. You can use, for example, that in processors and digital circuits. Okay, so this will be our focus in this course. So high voltage here will be, let us say, around 1 volt. That will be the digit 1, and the low voltage, which is around 0 volt, this will be the digit 0. So here you can see that, okay, the voltage level, which is used inside the electronic circuits, inside the digital circuits. Okay, so we have low voltage, that will be digit 0, and high voltage, which is digit 1. What I mean here by high voltage, I don't really mean actually very high. It means like around like 1.2 volts. That's it. Even today, modern processors, they are actually using voltage even below 1 volt, sometimes 0.7, 0.8 volts. That's actually considered to be high voltage. In the past, people used like 30, 40 years ago, people used actually 5 volts. Okay, so high voltage was around 5 volts. we don't really care too much about the voltage value, okay, or the voltage level. All what we care is that we are using actually here high voltage for 1 and low voltage for 0, okay? That's actually using electric voltage. We can use electric charge, okay? For example, inside the memory of a computer system. So inside a memory cell, inside the main memory of a computer, people use tiny capacitors. So when they charge the capacitor, they are storing a 1. And when they discharge the capacitor, they are storing a 0. So they use actually a very tiny electric charge to charge the capacitor and to discharge it. And this way, okay, you are storing, so if the capacitor is charged, we call it logic 1, and if the capacitor is discharged, they call it 0. Okay, so we can store the 1 and the 0 as an electric charge. Okay, you can actually have billions of these capacitors inside today a memory chip. We can use magnetic field. That's another way, a third way, okay, of storing a 1 or a 0. This has been used actually for like 6 decades. Since the 1960s, people have invented magnetic disks and even magnetic tapes, okay? But magnetic disks actually are very popular. So people, for example, store files on a magnetic disk. You can actually have an external magnetic disk, or you can have it even inside your computer system. So people use actually the magnetic field to store 1s and 0s based on the polarity, okay, of the magnetic field. They can actually store 1s and 0s. So on a magnetic disk, you can actually store billions of these bits on the surface of the magnetic disk, okay? So we are using here the magnetic field to store the 1 and the 0. Very simple, okay? The idea is simple. All what we need is just to store 2 possible values. Or even using light. People use light in optical disks, and they use optical lenses. And also they use sometimes in optical networks, okay? High-speed networks. They use light, okay, to transmit 1s and 0s, okay? And usually there is an optical lens that can sense the light, okay, whether actually, so it senses whether you are actually transmitting or storing, let us say, a 1 or a 0. So there are different technologies today, okay, that can represent the binary digit, the 0 and the 1. Is this clear?
Yes.
Students, are you with me?
Yes.
Okay, very good. So now we have seen actually different technologies, okay, that are used today to store the binary digit. So the binary digit is called the bit, okay? So bit means binary digit. So they take here the B, I, and the T, okay? That's actually is the bit, okay? It means either a 0 or a 1. So let me pause here, it's time. Okay, next time I'll talk more about the binary number system. I'll talk about number systems in general. So my topic today will be about binary numbers. Everything stored inside the computer system is in binary. So whether we are storing numbers or we are storing fractions or negative numbers, signed, unsigned, okay, characters, symbols, images, sound, everything is stored in binary. It's a lot easier to represent numbers in binary rather than in decimal, because the way that the digital circuits represent numbers in binary using only 2 voltage levels, okay, high voltage and low level to represent the 1 and the 0, makes it a lot easier to deal with binary rather than with the decimal number system. So we human beings, we are used to the decimal number system, but computers prefer to use the binary number system. So for this reason, I need to talk about binary numbers and how to convert between binary and decimal in great details. Okay, so this is my topic today. Okay, so remember that binary means 2. And a binary digit, which is also called a bit. So bit means binary digit. It can be either 1 or a 0. Now, let me just go here back, okay, and show you, okay, how we can represent a number in binary. Now, a single bit can only represent two values, 0 and 1. You cannot really do much with a single bit, but you can take a group of bits, for example, 8 bits to represent a number. So here I'm showing 8 bits, and these bits are numbered, okay, from bit 0 to bit 7. So bit 0 here is the least significant bit, and bit 7 is the most significant bit. So we start at 0, okay, so the least significant bit appears to the right, the most significant bit appears to the left. Since we start at 0, so the most significant bit will be 7 if we are using an 8-bit number. Now, each bit has a weight, okay, so it has a position and it has a weight. So the weight of bit 0 is 2 to the power 0, which is just 1. And the weight of bit 1 will be 2 to the power 1, which is 2. Then we have 4, 2 to the power 2 is 4, 2 to the power 3 is 8, then 16, 32, 64, and 128. So this is an 8-bit number, and each bit has a weight. So the weight depends on the position of the number, of the bit inside the number. Now we can, yes, go ahead. Question?
The last sentence, 7-bit.
No, we are dealing with 8-bit number, but we are numbering the bits from 0 to 7.
Yes, before this slide.
Yes.
Bit 7 in an 8-bit number.
So bit 7, yeah, well, this is bit 7 here, which is shown as the most significant bit. Let me use my highlighter. Okay, so I'm going to use a highlighter here. Okay, you can see this is bit 7 here, right? That's actually bit 7 that has the value 1. This is an 8-bit number. So the most significant bit is bit 7. The least significant bit is bit 0. So the bits are numbered from 0 to 7. Now this number consists of 8 bits. We call it a byte. Okay, so a byte inside the computer system consists of 8 bits. So you can use it to store an 8-bit number.
Yes,
okay.
Thank you.
You get it now?
Yes, thank you.
Okay, so now we can say what's the decimal value of a binary number. So each bit has a weight, and this weight is a power of 2. Okay, so you can see it here, 2 to the power 0. This is for bit 0, 2 to the power 1 for bit 1, all the way here to the most significant bit. Okay, so the most significant bit is bit 7, and the weight is 2 to the power 7. Now, if I would like to calculate the decimal value of a binary number, what I have to do is that I have to take each bit. So I'm calling it digit 0. The 0 here is bit 0. I have to multiply it by 2 to the power 0. Then we go to digit 1. Okay, that will be bit 1. It will be multiplied by 2 to the power 1, which is simply equal to 2. Then digit 2 will be multiplied by 2 to the power 2. 2 squared is equal to 4. All the way to the most significant bit. Now, if we have n bits, the least significant bit will be bit 0. The most significant bit will be bit n minus 1. So this is digit, okay, or bit n minus 1. So I write it dn minus 1. This must be multiplied by 2 to the power n minus 1. Here's an example of a number which is shown in binary. Now, this 1 here is just a 1. This is a 0 multiplied by 2. Multiplied by 2 is just 0. This 1 here must be multiplied by 4. This one is multiplied by what? What's the weight of this one? This one here is multiplied by what?
3.
8. Then this one will be multiplied. This will be what? This one will be what?
16. 2 to the power 4.
Okay, yes, 2 to the power 4 is 16. Then we skip the 0. We skip the 0. Now this one is what? What is 2 to the power 7?
128.
128. So I'm going to add 128 plus 16 plus 8 plus 4 plus 1. Now, if I do the math, if I add 2 to the power 7 is 128, 2 to the power 4 is 16, 2 to the power 3 is 8, This is 4 plus 1, you get 127. So this number here, which is shown in binary, it has the decimal value, which is 127.
Why did we skip the zeros?
This is the decimal value of a binary number. So if I would like to represent 157 in binary, I'm going to represent it as 1001 1101. Okay, that
Doctor?
will be the, yes, go ahead.
Why did you skip zeros?
Because 0 multiplied by anything is 0.
Oh, makes sense.
Okay, so 0 multiplied by 2 is 0. 0 multiplied by 32 equal to 0. 0 multiplied by 64 is equal to 0. Of course, you can actually add plus 0, plus 0, plus 0, but this does not change the value of the decimal number. Okay? So therefore, we only have 2 digits in binary, 1 and 0. If it is a 1, you look at the weight of the 1. If it is 0, you simply just add 0, so it does not really change the value of the decimal value of the number. Okay, is this clear? Right. So now it's actually important to remember some common powers of 2. If you would like to do it this quickly by hand, it's important to remember these powers of 2. So 2 to the power 0 is simply equal to 1. 2 to the power 1 is 2. Then we have 4, then 8, 16, 32, 64. 2 to the power 6 is equal to 64. 2 to the power 7 is equal to 128. So it's important to remember some of these common powers of 2. 2 to the power 8 is 256. 2 to the power 9 is 512. And 2 to the power 10 is equal to 1024. Now, this is interesting. Okay, when you look at 2 to the power 10, it's slightly more than 1000. It's 1024. So remember these powers of 10. You can go all the way here to 2 to the power 15, but I'm going to stop here. Okay. So it's common to remember these powers of 2 because we use them frequently when we are dealing with binary numbers and would like to obtain their decimal values. We would like to convert the binary number into decimal. Is this clear? Right. So the binary number system and the decimal number system are called positional number system. In the past, before people have invented the decimal number system, people have used, for example, the Romans have used the Roman numeral. So they used letters to represent numbers. For example, X here will be 10. So you have here 10, and you have another X, which is another 10. So this will be 20. And then the V will be 5. So this will be 25. And then the I will be 1 and another 1 here. So this will give you 27. So 10, 10, 20 plus 5, 25 plus 2 is equal to 27. Today, if you would like to write 27 in decimal, you write 2, 7. You know that this 2 here is positional, it's 20. And so this 2 must be multiplied by 10, so it becomes 20. Plus 7, it becomes 27. So this is the decimal number 27. So we use radix 10. Now, the meaning of radix 10, it means that we have 10 digits from 0 to 9. But you can write a number, okay, consisting of multiple digits, and each digit has a position inside the number. This is why we call it a positional number system. So the decimal number system is a positional number system because each digit in the number has a position and a weight. On the other hand, the Roman number system is not positional. Okay, you can write the X anywhere inside the number and the X is still 10. Whereas the digit here that you write in a positional number system has a weight. So this 2 is not a 2, it's a 20. Okay, and this 7 is just multiplied by 1. The binary number system, we call it radix 2 because we only have 2 digits, 0 and 1, is also positional. So this is the binary number system. Okay, so it's called binary because it's only 2 digits. So if you look here at this binary number, which is 11011, Okay, you can say, well, this is an example, 11011. This is just a 1, this is 2. Okay, this is 0 multiplied by 4 is just 0. This is 8, and this is 16. If you add them up, you get also 27. So 11011 is also 27. So this is how you present the 27. In binary, this is 27. In decimal, and this is 27 according to the Roman, okay, Roman, using the Roman numerals. Is this clear? Students, is this clear? So we can actually represent numbers in different number systems. Okay. Now, as I said, that computers prefer, okay, the binary number system, as we have seen last time, because it's easy to deal with only 2 digits only, 0 and 1. On the other hand, we are used as a human beings to the decimal number system. Do you know why we use the decimal number system? Any idea? Why did people invent the decimal number system? Why do you
because
think?
it's easier.
Yeah, why it's easier to deal with decimal?
Because
It's straightforward.
Because
You
you
don't
can-
have to recalculate it or something.
I mean, why people, why our ancestors have invented the decimal number system thousands
because
of
you
years.
can because you can represent big numbers with few letters.
No, we are talking about the decimal number system. Okay, so why did they invent decimal? Why they did not invent binary?
To be more accurate.
Why do you think that we have decimal number system actually until today? People have invented this hundreds of years ago, right?
Because
why do we have
want,
decimal? Why do we have 10 digits from 0 to 9?
Because, for example, if we wanted to write a number like 3000, if we will write it with the binary numbers, it will take like forever.
What I'm asking is, okay, why do you think that people thought about the decimal number system? Okay, in history, if you just go back to our ancestors, why did they invent decimal? Why it's natural to us?
اتوقع انه عشان يعطيك خيارات اكثر من البرايمري.
They could have invented binary from the beginning, ones and zeros, that's it. Why did they invent decimal? Why?
Because you can use a scientific method. Scientific notation, I mean.
No, the answer is simple, because we have 10 fingers. Okay. We have 10 fingers. If you look actually at, if you would like to teach a child to count, you teach him to use his fingers, okay? So people actually use their fingers to count, and because we have 10 fingers, they thought about the decimal number system. Okay, it's that simple. Because we have 10 fingers, this is why the decimal number system is natural to us, okay? If we only had 2 fingers, then we would have used actually binary. It's that simple, okay? So this is why the decimal number system is natural to us, because we have 10 fingers, okay? Let us take a look at this number. Now you can actually use any number system, okay? For example, the octal number system. The octal number system has only 8 digits from 0 to 7, okay? Only 8 digits. If we had only 8 fingers, we would have used the octal number system. So we can actually count from 0 to 7. Okay, we'll only have actually only 8 digits. So for example, this number 2107 in octal, you see that I'm writing 8 here? That actually is the radix. So 2107 in octal, what is the value? What's the decimal value of this number? Any idea? What is the decimal value of 2107 in octal? Well, just use this equation here.
Is it a mix between the 2 equations?
Use this equation. You know, this is the equation. What is the radix r? The radix r is 8. Okay. What is d0? It is 7. What is d1? It is 0. What is d2? Is 1. What is d3? It's 2. So we have here 4 digits. Digit 0, digit 1, digit 2, digit 3. Now this is in octal. So we are using the octal number system. So we have only the digits from 0 to 7. So if you look at this number here, 2107, this is 7 multiplied by 1. This is 0 multiplied by 8. This one is multiplied by what? This one here is multiplied by what?
8 to the power 2.
8 to the power 2. Yes, it's 64. And this 2 is multiplied by what?
8 to the power 3.
Yes, it's 8 to the power 3. So just do the math and you will get the number 1095. So the decimal value of 2108 in octal is 1025. So we can do a conversion between different number systems. Okay. So in octal, this is not 2107 because this is not decimal. This is not 2000. It's not 1000. It's 2 multiplied by 8 to the power 3 because the radix or the base here is 8. And the position of this digit is actually at position 3. So we multiplied by 8 to the power 3. This one is multiplied by 8 squared. This 7 is multiplied by just 1. So therefore, we get the number 1095. So this is in decimal. So when we say 1000, it means 1 multiplied by 10 to the power 3. When we say 95, this 9 is multiplied by 10 to the power 1. And this 5 is just a 5. Notice that there are 0 hundreds. This is the importance of the 0. If there are no hundreds, we write a 0 at this position. So it's 0 multiplied by 100. Okay? So it's 1095. There are no hundreds here. Okay? Is this clear? This is what I mean by the positional number system. You can choose whatever radix. So in decimal, the radix is 10. We have 10 digits. In binary, the radix is 2. But we can also use actually another radix. I can choose the radix to be 8, like in this example, or I can choose the radix to be, let us say, 5. Okay. So we can actually choose the radix to be actually 8, 5, 2, 10, whatever. Okay. So the math applies actually to any radix. That's why we call it a positional number system, because each digit has a position in the number. Let us move on. Now, to convert, okay, so to convert actually the number in any radix to decimal, we use this equation, which is shown here in yellow, okay? So D0 is just digit 0, D1 is multiplied by the radix R, D2 is multiplied by R squared, all the way to the n-1. This will be the most significant digit. It's multiplied by R raised to the power n-1. Of course, depending on the value of n, okay? The number of digits inside the number. How about if I would like to convert a decimal number into binary? How do I do this? If I have a number in decimal, how do I convert it to binary? Any idea?
We can divide the number by 2 and take the modulus.
Yes, we can look at the remainder. Exactly. This is the procedure. So let us take a look at it. So what we need to do, if I have a number in decimal, it's difficult really to guess the number in binary. We need a method, okay, to convert the number in decimal to binary. And this method is simple. All what we have to do is we have to divide the number in decimal by 2. Now, why do we divide it by 2? Because the radix is 2. Okay, because we would like to convert it to binary. So binary means the radix is equal to 2. Let us take a look at this example. Now, when we divide a number by 2, you get a quotient and you get a remainder. This is integer division. Okay, so what we have to do is that we have to look at the remainder. Okay, so the remainder here can be either 0 or 1. Okay, when you divide a number by 2, you can only have two possible remainders, either 0 or 1. If the number is even, the remainder will be equal to 0. But if the number is odd, then the remainder will be equal to 1. Let us take a look at this example. Suppose I would like to convert 37. Now this 37 in decimal, I'm writing 10 here to emphasize that this 37 is decimal, okay? I would like to convert it to binary. So in order to convert the number 37 to binary, I'm going to divide 37 by 2. Now, when you divide 37 by 2, you get 18, okay? In fact, you get 18.5. But since we need to do integer division, so the integer part is 18, but you multiply 18 by 2, you get 36. You see 36, you can say 37 minus the 36, the remainder is equal to 1. So this is how we calculate the remainder. In fact, you can see that the remainder is equal to 1 because the number is odd. 37 is an odd number. It's not an even number. So this is the remainder. Now this will be the least significant bit. We take the 18 and divide it by 2, we get 9, and the remainder is 0. Take the 9, continue dividing it by 2, you get 4, and the remainder is 1, because actually 9 is odd. Take the 4 and divide it by 2, you get exactly 2, and the remainder is 0. Okay, take the 2, continue. So basically, we continue to divide the quotient by 2. You get 1, and the remainder is 0. Take the 1 and divide it by 2. Now, 1 is less than 2. Okay, so when you divide 1 by 2 and the dividend, so here we have the dividend is less than the divisor. Okay, so 1 is less than 2. You get 0 as a quotient, and the remainder is equal to 1. Okay, so you can see that the remainder is equal to 1, which is basically the one that appears here on top. Okay, so therefore this is the dividend, okay, which is equal to the 1, the divisor equal to 2. So basically when you divide 1 by 2, you get 0. So 0 multiplied by 2 is 0. And therefore when you subtract, you get the remainder is equal to 1. Now when we stop when the quotient is equal to 0. Khalas, we don't really continue. So now we can see that we can say that the least significant bit is equal to 1. The most significant bit here is this one, and we stop when the quotient is 0. So I can write now that 37 can be written in binary. Now we write it backwards. So this one appears here. Okay. If I would like to draw an arrow, okay, let me use here my pen tool. Okay, so you can say that this one here is this one here. And this is the most significant bit which appears here, okay? You can see that clearly. So basically the remainder, okay, are the bits of the binary number, and we write them backwards, starting from the least significant bit to the most significant bit, okay? So the number can be read as 100101, and this number is 37, okay, in decimal. In fact, you can convert it back from binary to decimal to check that your conversion was done properly. So if you add 1 plus 4, you can skip these zeros. So this will be 1, this is 4, this is 32. So 32 plus 5 is equal to 37. So therefore, the conversion was done properly. Is this clear? This is basically the conversion procedure. You can take any number in decimal and we can convert it to binary. Okay?
Doctor,
what if the decimal number is 37.6 or 0.7? The answer would be the same, yes?
Well, if you have a fraction, then the fraction has to be converted separately. Here I'm talking about an integer, okay? It does not really have a fraction. So we are talking, I'll talk about fractions later, and I'll talk how we can represent fractions in binary That's a different topic. I did not talk about fractions, so the focus is on integers. So I said here, okay, converting a decimal integer, right? It's an integer. Remember that, okay?
Okay.
If it's a fraction, it's a different procedure.
Okay.
Okay, I'll come back to it later. Right. So fractions will be my topic,
Doctor?
inshallah, on Thursday. I'll talk about
Doctor?
fractions. Fadal.
I think there is another way, but I'm not sure. So 32, if I wanted to convert it, I need 32 plus 4 plus 1, right? So
this will
I
be
can.
guessing. This will be guessing.
Yeah.
Okay. Yes, of course you can do it this way. You can actually guess the weights and the bits. Okay. You can say that actually, okay, what is the near? So 37. You can say that 32 is close to 37. So you subtract. Okay. And you see when you subtract 37 minus 32, the remainder is 5. So you see that 4 is close to 5. So you subtract, and what is left is 1. So you can say that 37 is 32 plus 4 plus 1, but this will be guessing. Okay, this guessing will work if you are dealing with small integers, but if you are dealing with large integers, you need a procedure, a method that will discover the. Okay. Okay, so now let us move on. Okay, so if I would like to convert from decimal to binary, what I have to do is that I have to divide. So my number n here, okay, is in decimal. I can actually write it. I can expand it like this. So I can say this is digit 0, or bit 0 must be multiplied by 2 to the power 0. D1 is multiplied by 2 to the power 1. D2 is multiplied by D2 squared, and so on. Now, if you divide this n by 2, okay, you divide actually everything by 2. Now, D1 multiplied by 2 divided by 2, you get D1. D2 multiplied by D squared divided by 2, you get D2 multiplied by 2. And Dn minus 1 multiplied by 2 to the power n minus 1 divided by 2, you get 2 to the power n minus 2. Now, D0 is just multiplied by 1. So the remainder becomes D0. So when you divide n by 2, you get the quotient. This will be the first quotient. Quotient 1 is equal to this number here, and the remainder 1 is equal to D0. So we have discovered the first remainder, which is the least significant bit of the number. Now you take this quotient 1 and divide it again by 2, you get quotient 2. And you get the remainder 2, which is equal to D1. So this D1 becomes the second remainder. And you continue dividing by 2 until you have discovered D2, D3, all the way to Dn minus 1. So you discover all the bits of the number. So this is actually a mathematical proof that the method works, okay? So this is why we divide by 2. And this is how we obtain the bits of the binary number, okay? So D0, D1, D2, D3, and so on, these are the remainders. So the first remainder is D0, the second remainder is D1, and so on. And these are the digits or the bits of the binary number. So this is why we continue and repeat dividing the quotient by 2 until the quotient becomes 0. So we stop when the quotient becomes equal to 0, okay? And the remainders will become the bits, okay, of the binary number. And we have the first remainder will be the least significant digit, and the last remainder will become the most significant digit of the binary number. Okay, so this is basically an explanation why the division by 2 is the method to obtain the bits of the binary number. Now, there are some popular number systems that people use. We have seen that for computers, we have to use the binary number system, and the radix is equal to 2. However, we as human beings, we use the decimal number system, and decimal means that the radix is equal to 10. That actually is the decimal number system. So computers, okay, need to use the binary, which is radix equal to 2, because it's easier to design the circuits, okay, using the binary number system, whereas us as a human beings, we are used to the decimal number system because our ancestors, okay, have discovered, okay, the decimal number system by using their fingers, okay, by counting using their fingers. This is why decimal is natural to us, whereas binary is more convenient to computers. Now we can actually use other number systems. Mathematically, you can use any number system. For example, the octal number system, the radix is equal to 8. So 8 means octal, okay? So octal here means that we have 8 digits, and these are from 0 to 7. We always start at 0, and we stop here at the radix minus 1. So the radix is 8, so therefore we stop at 7. In 10, we start from 0, and we stop at 9, okay? Now notice that 10 consists of 2 digits, 1 and 0. So therefore, if you want to write the number 10, you have to write it as 1, 0 in decimal. In the case of 16, we call it the hexadecimal number system. So hexadecimal, it means that the radix is 16. So in the case of 16, we have to use the first 10 digits, okay, in decimal from 0 to 9. So these are from 0 to 9. But we need 6 more digits. But there are no more decimal digits because there are only 10 decimal digits. So therefore, we use letters as digits. So now we use letter A becomes 10, B becomes 11, C becomes 12, okay, D becomes 13, E becomes 14, and F becomes 15. So therefore, we use 6 letters from the alphabet as, as digits in the hexadecimal number system. So therefore, we have to refer it to a single digit. Okay, we cannot write it as 1, 0. So we have to write A, and A will be the digit 10, and B will be the digit 11, and F will be 15. So you have to remember these in the case of hexadecimal because we are using 16 digits. So we need 6 extra digits, and we use them as letters. Now, there is an easy way to convert between octal and hexadecimal number systems and binary because they are related. So people, programmers, okay, when they are programming, rather than using binary, it's actually easier for them. It's actually more convenient to them to use octal and hexadecimal. Now, octal is 8, and 8 is 2 to the power 3. Hexadecimal is 16, and 16 is 2 to the power 4. So there is an easy way to convert between binary, octal, and hexadecimal. Let us take a look at this. Now, this table here shows, okay, the binary, octal, hexadecimal, as well as decimal. These are the most popular number systems. Okay, so I'm showing here, okay, the decimal values, okay, starting from 0 all the way to 9. This will be a single digit, okay, in decimal. And then I'm going to 10, 11, up to 15. Now, the reason why I'm going to 15, because I can represent it with a single digit in hexadecimal. So in hexadecimal, 0 to 9 are exactly the same way, 0 to 9 in decimal. So here we have it 0 to 9, and here I have it 0 to 9 in hexadecimal. They are identical to the digits in decimal. But 10 is written as 2 digits in decimal. We can write it as a single digit in hexadecimal. So 10 will be A, 11 will be B, and we can go all the way here to 15. 15 will be F. Okay, is this clear? These are the 16 digits in hexadecimal. In the case of binary, we need actually 4 bits to represent the decimal values from 0 to 15. So 0 will be in binary. If I use 4 bits in binary, 0 will be 0, 0, 0, 0. Okay, 1 will be 0, 0, 0, 1. 2 will be 1, 0. Okay, 0, 0, 1, 0. So that's 2. 3 will be 0, 0, 1, 1. 4 will be 0, 1, 0, 0. This one will be 4. This is 5, and so on. And finally, 15 will be 1, 1, 1, 1. Notice that this is 8 plus 4 plus 2 plus 1. This will give you 15. Notice that 10 is 1, 0, 1, 0 in binary. This is 8 plus 2 will give you 10. Here 9 will be 1001. That's 9. It's 8 plus 1. 8 is 1000. This one is the 8. Okay? Is this clear? Now, this table is so important when you would like to do the conversions between binary, octal, hexadecimal. You can do it very quickly using this table. Okay? Now, notice that in octal, we only have 8 digits from 0 to 7. Okay? So these are exactly the same 8 digits that exist in decimal. So we go from 0 to 7. But there is no digit which is 8. So 8 will be 10 in octal. So 10, this is not 10. This is 10 in octal. So 10 is 8 because this one is multiplied by 8. 9 will be 11. It's 8 plus 1. So the most significant digit here is 1, which this most significant digit is the 8, and the least significant digit is the 1. So 8 plus 1 is equal to 9. And finally, here we have 17. It's actually 8 plus 7. So this 17 is not 17. It is just 17 in octal, which is 8 plus 7, which is equal to 15. Okay? Is this clear? So it's very important to remember this table because we can easily do the conversions between octal, hexadecimal, binary. We can do this kind of conversion very quickly. Right. Let me show you an example how we can do the conversions between these number systems. So remember that radix 16 is 2 to the power 4, okay? And radix 8 is 2 to the power 3. So this is why we chose 16 and 8, because they are related. They are power of 2. Now, because they are power of 2, as we have seen in the previous table, in the previous slide, okay, we can represent every hexadecimal digit with 4 bits. And we can represent every octal digit with 3 bits. Why? Because octal, we only have radix 8, 2 to the power 3. So we can use 3 bits to represent a single octal digit. Suppose I would like to take a number. Okay, so given this number, which is shown in binary. Okay, so this is a 32-bit number in binary. You can actually count the bits. If I would like to convert this number to octal, how do I do this?
We can divide the number into 3 bits. For example, we take 33 bits from the right and convert them to the equivalent.
Exactly. So yes, this is what you are saying is correct. We have to group the bits, but we start from the right, from the least significant bit. So I'm going to look at this 100, right? So this is a group of 3 bits. So what is 100? What is 100 in octal?
4.
What is 100? It is 4, yes. In decimal, it's also 4, and octal will be 4. So therefore, we say that we take a group of 3 bits, starting from the least significant bit. So we start from the right. It's very important to start from the right, not from the left, because if you do it from the left, it will be totally wrong. So you have to start from the right. So 100 will be 4. Next, we have 010. It will be what?
1.
010 is what?
2.
2. Yes. 110.
12. 6.
110. 6.
5.
Yes.
5.
011.
5.
011.
3.
No mistakes, please. No mistakes. 010.
4.
010.
2.
5.
Yes, 2. 101.
5.
Yes, 5.
5.
101 again.
Another 5.
Okay. 000.
0.
0.
Okay.
0.
011.
3.
01.
5.
Okay. Finally, we have 11. Now these are only 2 bits, but we can always insert a 0 from the left. It becomes 011. Is what?
3.
Good.
3.
Good.
3.
I'm getting a echo for my voice. Right. Suppose I would like to convert it to hexadecimal. Okay, to hexadecimal. How do I do this?
4 bits.
We take
group
4
within 4.
bits.
4 bits. So now I have to add, so it will become 0100. What is 0100?
Still 4.
Yes. Again 4, yes. 4 in hexadecimal. Then I have 1001. I have to take 4 bits.
9.
9. Yes. You see, this is why it's very important to remember the table that we have seen in the previous slide, so that we can do the conversion very quickly. Okay. So 0111 is what?
7.
Yes. Next, 1010.
11.
1010.
10.
10. What is 10? What is 10 in hexadecimal?
8.
It has to be represented by a single digit. How about 0110?
11. B.
0110.
6.
Oh yes, it's 6.
6, right. 0001. Please,
One.
let's go.
1.
Okay, next we have 1011.
This is 11.
11.
11.
What is 11?
B.
B. And finally we have 1110.
E.
Yes, it's 14. It is E. Exactly. Good. So now you understand how we can do these conversions quickly between octal, hexadecimal, and decimal. Okay. Right. If I would like to convert octal to decimal, this is very easy. All what we have to do is that we have to use the formula which is shown on top. So I have this number which is 7204 in octal. I would like to convert it to decimal, no problem. This is actually 4 multiplied by 1. This is just a 0. This 2 is multiplied by 8 squared, and this 7 is multiplied by 8 cubed. You use a calculator, you do the math, you get 3,716. Now, this is not 7,204. This is just 7204. This is how I read it. 7204 in octal is 3,716 in decimal. Let us take a look at this number. Now, this number is in hexadecimal. So you can also have digits like A, B, up to F. Now, this 3 is multiplied by 16 cubed because it has this position here. This B is 11, and it's multiplied by 16 square. This A here is the 10. It's multiplied by 16, only 16 to the power 1, and this is just a 4. If you add them up, you get 15,268. Okay, is this clear? That's how we do the conversion to decimal. You can just take a number in any radix, just use the equation and evaluate, and you get the number. However, if I would like to convert the decimal to hexadecimal, I'm running out of time. What you have to do is, how do I convert decimal to hexadecimal? We can divide by 16. We can divide by 16. Anyways, I'm running out of time. Let me just pause here. Next time, inshallah, I will talk about this. I will finish this topic. I'll talk about fractions. Do you have any questions, students? Do you have time? So there are some important properties that we need to know about number systems. So the first question is, how many possible digits can we have in radix R? How many possible digits can we have in radix R? Pick any radix R and get, what is the number of possible digits? Anyone?
R.
R, exactly, R digits. What are these?
0 to R minus 1.
From 0 to R minus 1, yes, R digits. So for example, if we are dealing in binary, we have 2 digits from 0 to 1. If we are dealing in decimal, it will be 10 digits from 0 to 9. Excellent. So what is the result of adding 1 to the largest digit in radix R? What is the result of adding 1 to the largest digit in radix R?
Return back to the smallest digit.
Yeah, for example, if we are in binary, let us take decimal. Decimal is easier. So what is the largest digit in decimal?
9.
Okay, if you add 1.
You are 0, 0, 1.
It will be 10. 10 is written as 1, 0, right?
Yeah.
So it will be 1, 0 in radix R. if you are in binary, the largest digit is 1. If you add 1 plus 1, what do you get?
0 and 1 carry.
Yeah, so you got 1 0. So 2 will be 1 0 in binary, exactly. So 0 and the carry. So we write it as 1 0. Right. So therefore, since our digits, so we don't have the digit r in radix r. So if you add 1 plus the largest digit, you get 1 0 in radix r. Okay. Here are some examples. 1 plus 1 in binary will be 1 0. So 1 0 in binary will be 2. If you add 7 plus 1 in octal, you get 8, but 8 is 1 0. Okay. If you add 9 plus 1 in decimal, you get 10, but 10 is also written as 1 0. If you do it in hexadecimal, if you add f is 15, you add to it plus 1, you get 16, and 16 is written as 1 0 in hexadecimal. So you see that we are getting 1 0, but 1 0 has different meanings. In binary, 1 0 is 2. In octal, it is 8. In decimal, 1 0 is 10. And in hexadecimal, 1 0 is 16. Is this clear? So we write it 1 0, but it has actually a different value in different number systems. Clear? Is this clear?
Yes, it's clear.
Yes, clear.
Okay, very good. So now let me just ask you this question. What is the largest value using 3 digits in radix r? Yani, for example, if we are using decimal, what's the largest number that you can represent it with 3 digits?
It's the summation of
999.
Exactly, 999, 999. Yes. Okay, if it is in binary?
111.
If it is in octal?
777.
If it is in hexadecimal?
15.
F. We write F. Okay, exactly. Now, 999 is equal to what? 999, we can write it as 10 to the power 3 minus 1. Okay, it's 1000 minus 1. You agree?
Yes.
Right. 111 in binary, it's equal to the value of what?
2 to the power 3 minus 1.
It is 7. 7 is actually 8 minus 1. 2 to the power 3 minus 1. And if you look at octal, 777 will be 2 to the power, it will be 8 to the power 3 minus 1, and so on. So if you look here, for example, in binary, 111 is written as 2 to the power 3 minus 1. 777 in octal, it's 8 to the power 3 minus 1. And in decimal, 999 is 10 to the power 3 minus 1. So you can see it's the radix here. The radix raised to the power 3, because we are using only 3 digits, minus 1. So for any radix r, you can see that the largest value using 3 digits will be r to the power 3 minus 1. Okay? Is this clear?
Yes, clear. That's one.
Okay. So let us move on. Okay, how many possible values can be represented using n binary digits? If I use n binary digits, how many possible values you can have?
2 to the power
to the n.
Yes. So it's actually 2 multiplied by 2 multiplied by 2, because each digit in binary can have 2 values, right? So it's 2 multiplied by 2 multiplied by 2 n times. It's 2 to the power n. So we have 2 to the power n values. The smallest will be 0, and the largest will be 2 to the power n minus 1, because we started at 0, then the largest will be 2 to the power n minus 1. But if you use n octal digits, how many possible values you can have if you use n octal digits?
8 to
n minus 1.
8 to the power
n minus 1.
So you start from 0, you end at 8 to the power n minus 1. Yes. And how about if you use n decimal digits?
10 to the n minus 1.
It will be 10 to the power n values. You start at 0 and you end at 10 to the power n minus 1. Exactly. How about n hexadecimal digits?
16 to the n minus.
Yeah, so the total values will be 16 to the power n. The smallest will be 0. The largest will be 16 to the power n minus 1. Of course, we are not really counting here. We are not really dealing with negative numbers. We are dealing only with unsigned integers. I'll talk later about negative numbers because this will change. You can use binary numbers to represent also negative values. But I'll talk about these later. Okay, I'll come back to them later. So here we are dealing with unsigned integers. Okay, make it like this. طيب. Now, let us. Can you see me or okay? I need to turn on my camera. Can you see me now?
Yes.
Yes.
Yes. Okay.
Yes.
Good. Right. So that's actually, these are important properties of number systems. If you'd like to use n digits in radix r, okay, how many possible values can be represented?
R values.
R to the power.
R to the power.
R to the, exactly, R to the power n. The smallest will be 0, the largest will be R to the power n minus 1. So this is the rule, okay? Right. Now I would like to talk about how we represent fractions, okay? Representing fractions. So far I talked about unsigned integers. So let us talk about fractions. Now you can represent a fraction, okay, in binary. The same way that you can represent a fraction in decimal, you can also represent a fraction in binary or in any number system, okay? So we use the position of the digit inside the number to specify the weight of that digit. So if you have a number n in radix r, it can also have a fraction part. So I can write it like this. So you can see that the integer part appears before the point. Now this is what I call it the radix point, okay? In decimal, we call it the decimal point. In binary, we call it the binary point. And the rest here will be the fraction. So we write the integer part, then we write the dot or the point, and then after that we write the fraction. So remember to use the dot. Okay, we don't use the comma like we do in French or Arabic. We use the comma to specify the fraction. No, we use the dot. So make sure in the exam or the quiz, you make sure that you write the dot. Okay, and everything after the dot will be the fraction. Okay, is this clear? Understood? Now, okay. So please make sure that you use the dot. So d minus 1 here indicates the first digit in the fraction. D minus 2 will be the second digit in the fraction. And d minus m, it will be the m digit in the fraction. So notice that I'm using minus 1, minus 2, and minus m. I'm using here a negative position. And the reason why, because these digits exist in the fraction. Whereas in the case of the integer part, we start from 0, 1 up to n minus 1 when we have n digits in the integer part. But in the case of the fraction, we start with negative 1, negative 2. So this indicates the position of the digit in the fraction. And we can use this to specify the weight. Okay, so this is the integer part, this is the fraction part, and this is what we call the radix point. If this was decimal, it will be the decimal point. If it was binary, we call it the binary point. Okay, so it separates the integer part from the fraction part. Now we can always write the value, okay, of the number n in radix r. So in the case of the integer part, we start here at d0 is the least significant digit. d1 will be multiplied by r, d2 will be multiplied by r squared, and so on. In the case of the fraction, we take d minus 1. This is the first digit after the point. It's multiplied by r to the power negative 1. In other words, we are dividing d by r. D minus 1 is divided by r. R to the power minus 1 is division by r. So I'm using a negative exponent. Okay, so when you multiply by r to the power negative 1, it's the same thing as division by r. D minus 2, that will be the second digit in the fraction part. It's multiplied by r raised to the power negative 2. So we are dividing by r squared, and so on. So the last digit in the fraction here, d minus m, is multiplied by r to the power negative m. For example, if this actually number was in decimal, then r will be 10. The radix will be 10. So the first digit in the fraction will be divided by 10. The second one will be divided by 100 and so on, okay? If this were in binary, then R will be 2. So it will be 2 to the power negative 1, 2 to the power negative 2, and so on. So we can write it in sigma notation as a summation. This is the integer part. I here is the index, or if you would like, the position of the digit. So I starts from 0 to n minus 1 di here. These are the digits that exist in the integer part. We multiply them by r to the power I. And then this is the second summation here, okay, which is written in sigma notation. It's for the fraction part. So dj here is the digit in the fraction. I'm using here j from -1 to -m. Of course, here -m will be the smaller value, -1 will be the larger value. So I'm writing them in this order. Anyway, it will be dj multiplied by r to the power j, but the exponent here is negative, indicating the fraction part. I have examples about how to represent fractions. Here's an example in decimal. Okay, so you can see the number here is 2,409.87. Now this 2 is multiplied by 1,000, 10 to the power 3. This 4 is multiplied by 100. This 0 is multiplied by 10, but 0 multiplied by 10 is 0, so I'm not showing it. This 9 is multiplied by 1. Now this 8 is divided by 10. This is actually in the fraction. So I'm multiplying it by 10 to the power -1, and this 7 is divided by 100. So this is why I'm multiplying it by 10 to the power -2. Okay? So here's an example of a number which is in decimal. I can do exactly the same way in other radices and other number systems. For example, in binary. In binary, we only have 2 digits. So you can see that this one is what? This one here, the most significant one is what? Can anyone answer this question? Let me use here my highlighter.
1 multiplied by 10.
1 multiplied by 2 to the power 3.
See, this is 2, right? Radix
Yes.
2. So this one is what?
Multiplied by 2 to the power 3. 1 to the power.
Which is what?
8.
8. Yes.
So this one is 8. This one is what?
4.
4.
This one is what?
2.
0 and 2.
1.
It is just
1.
1. Yes.
We have here 0 multiplied by 2. This is just 1 multiplied by 1 is just 1. How about this one?
1 over
It's -1.
1 over 2.
It's half. Yes, it's
1
1
over
divided by 2. How about this one?
1 over 8.
No, this is 1 over 2, 1 over 4, 1 over 8. This must be what?
1 over 16.
1 over 16, exactly.
Yeah.
So all what you have to do is just add the weights. And if you add the weights, this is actually 2 to the power 3. This is 8. This is 4. This is 1. This is half. This is 1 over 16. You get 13.5625. So the decimal value of this binary number is 13.5625. Is this clear?
So after the binary digit, we start from -1, not from 0.
So the fraction, the first digit after the binary point will be the first digit in the fraction. It will have the weight -1.
Okay.
2 to the power -1. Then yes, so 2 to the power 0 is for the integer part. So the digit 0 is here.
Yes.
The fraction we start with -1. Yes, we start with -1.
Okay.
I have more examples. Let us take a look at this one. So this 7 here is multiplied by what?
By 8 to the power 2.
Yes, by 8 squared, which is 64. So we have to multiply 7 by 64. This 3 is what?
3.
It is just 3. It's unit, right?
Yes.
How about actually this 6?
6 over 8.
6 over 8.
6 over 8. How about this 4?
4 over
64.
64, yes.
Yes, we divide by 64. Or we multiply by 8 to the power -2.
Yes.
So if you do the math, you get 451.8125. So you can always convert from any number system, okay, from binary, from octal, from hexadecimal. It does not really matter, to decimal, using just the equation that we have seen in the previous slide. I have more examples. Let us take a look at this one. This is hexadecimal. So what is A?
10.
10 multiplied by what?
10 multiplied by 16 to the 3.
16 to the power 2.
To the
Two
power
or
2,
three?
yes.
Two or
Two.
three? Two, yes,
Two.
because we start here at 0. Okay,
Yes.
so this a here must be multiplied by 16 squared. 16 squared is 256. Now this one is multiplied by what?
16 to the
16.
1 to 16.
16, and this f is what?
Just 15.
Now this 8 is what?
8 over 16.
Yes, 8 over 16, which is just half. So if you do the math, you get 2,591.5. That's the decimal value of this hexadecimal number. So you can see that numbers can have a fraction. Okay, they can have a fraction. I also have more examples. How about this one? Now you see that here I'm using radix 5. Although radix 5 is not really common, what is common is actually decimal and binary. And we have seen that octal and hexadecimal are related to binary because 8 is 2 to the power 3 and 16 is 2 to the power 4. But 5 really is not related, okay? But this is just an example to illustrate how we can do the conversion. So it does not really matter. You can choose whatever radix you want. So this 4 is multiplied by what?
25.
By 5 to the 2.
5 squared, right? Which is 25. How about this 2?
10 multiplied by 5.
Yes, and this 3?
3.
Only 3.
3, yes.
3. How about this one?
1
1
over 5.
1 over 5, which is 0.2. So if you do the math, you get 113.2. How about this number?
So multiply 6 to the 2.
Okay, so it's 2 multiplied by what?
By 6 to the 2.
6 to the power 2.
6 squared, right?
6 squared.
Yeah.
Okay.
Okay, then what?
Then 6 multiplied by 6,
By
which is
6.
36.
6
And
multiplied
then
by
3.
6.
Can it be
And
6?
Is this number allowed?
No,
Doctor.
it can't be 6.
Can we have
Because-
digit 6 in radix 6?
No, R minus 1.
Exactly. So this digit should not exist. So therefore, this number is wrong. In other words, this is a trick. Okay, if you get something like this in the exam, don't convert it. Write that this number cannot exist in radix 6 because the digit 6 does not exist. The largest digit that you can have in radix 6 is 5. You can have from 0 to 5, but not 6. So this number is illegal. Okay, it cannot exist. It's a wrong number. Okay, it's you cannot really have the digit 6. So digit 6 is not allowed in radix 6. Okay, this is actually just an example to illustrate that. Okay, that you should not really write such numbers. Okay, let us move on. Now, how about if I would like to convert a decimal fraction to binary? How do I convert a decimal fraction to binary?
Multiply by 2.
Oh, yes. If it were an integer, I would divide by 2. But because it's a fraction, I'm going to multiply it by 2. Exactly. So what the solution is to multiply n by 2 repeatedly and collect the integer bits. So for example, when I multiply 0.6875 by 2, I get 1.375. So this one here is the first bit that appears in the fraction. That will be the first fraction bit. Now we take the new fraction, which is 0.375, and multiply it again by 2. We get 0.75. So the 0 here, fraction. We take the 0.75 and multiply it by 2, we get 1.5. So this one here is my third fraction bit. Now we take only the fraction, which is 0.5 multiplied by 2, we get 1.0. So this one will be my fourth fraction bit. But now the new fraction is 0.0, so stop when the new fraction is 0.0. So this is the first fraction bit, this is the last fraction bit, and we stop when the new fraction is equal to 0.0. Now sometimes, because it's a fraction, unlike integers actually conversion will always stop. But in the case of a fraction, this might go forever. Yani you might actually have an infinite number of bits in the fraction. So we stop when we have enough fraction bits. Sometimes I only need, let us say, 10 fraction bits or 20 fraction bits. So there is no need to continue forever. Yani there are examples in which this conversion procedure does not end. So you terminate when you have sufficient fraction bits. So
and
in
how
this
will you
example,
decide?
so in this example, 0.6875 is equal to 0.1011 in binary. If you would like converted back from binary to decimal, you will get exactly 0.875. This one will be 1/2. Here we have 0/4. Here I have 1/8. Here I have 1/16. If you add half plus 1/4 plus 1/16, you will get 0.6875. As I said, that this procedure might not terminate. So therefore, the question will tell you, you will get an approximation, not an exact fraction, because fractions, okay, might actually go forever. Okay, so some numbers cannot be represented exactly in binary as a fraction, not as an integer. Integers can be represented exactly, but fractions might not be represented exactly in binary. So we stop when we have sufficient number of fraction bits. Is this clear? Someone had a question.
Yes, it's clear, doctor. But my question was, how will I decide when to terminate or when to stop?
Well, the question is, okay, so that actually depends on how many bits you would like to store in the fraction. Okay, so for example, numbers that are that have fractions that you would like to represent will have a specific number of bits in the fraction, depending, of course, on the amount of memory that you would like to use for the number. So if you are using a specific number of bits, then you stop when this number of bits have been reached. Okay.
Okay.
So
And,
this has to be specified in the problem itself, in the problem statement. Or when you reach 0.0, if the new fraction becomes 0.0, then there is no need to continue because all the remaining bits in the fraction will be all zeros. And you can actually write here infinite number of zeros in the fraction. It does not really change the fraction.
Yeah, that's obvious.
Okay.
Doctor.
Yeah. Yes, Fadda.
What if the number is 25.6875?
Okay, I'll talk about this. You convert the integer part separately and the fraction part separately. I have an example about this. Let us continue.
One more observation, doctor, if you may.
Yes.
For the fraction side, the numbering or the most significant will be from up to down, not like
right. So we go from
right?
left to right. We go from left to right. So therefore, the first bit that we have discovered is the first bit after the binary point.
Okay.
So we start here from
the
left,
integer.
unlike the integer. From actually the integer, we go from right to left.
Okay.
Yes, it's a good observation. Yes, it's true. If you want, you can always verify that your conversion was done properly. Take the fraction in binary, which is 0.1011, and then convert it back to decimal and see if you get 0.6875. Okay?
Yes, okay. Thank you.
Now, you can actually do this in any radix R. Yani if you have, for example, in number n, okay, and you would like to convert it, okay, to a fraction to a radix R, what you have to do, what we have done in the previous slide is that we converted to binary, which is radix 2. So we multiplied by 2. But if you would like to convert it to radix R, okay, what you have to do is that you have to discover d minus 1, d minus 2, d minus, all the way here to d minus m, but these are in radix R. So rather than multiplying n by 2, we multiplied by r. R is the radix. Okay? We multiply n by r, and we continue here. So when we multiply n by r, I discover d minus 1. Because if you multiply everything here by r, so r minus 1 multiplied by r will give you d minus 1. Now here d minus 2 will be multiplied. This was r minus 2 multiplied by r becomes r minus 1 and so on. So d minus 1 here will be the first digit, okay, in radix r appearing in the fraction. Okay, so it will be the first digit, okay, in the fraction appearing in the in radix r, and then we take the fractional part and then we repeat to obtain d minus 2, d minus 3, and so on. And we stop when the new fraction becomes 0.0 or when we have sufficient fraction digits, because this procedure might not terminate. Okay. Let me show you more examples. Okay, these are more conversion examples. Suppose I would like to convert to octal. So this number here is in decimal, 139.6875, and I would like to convert it to octal. How do I do this?
Convert the integers alone and the decimals alone. The integers, you will divide them by 8, and the decimals, you'll multiply them by 8.
Diffraction, we call it diffraction. Yeah. What appears after the decimal point, we call it diffraction, yes. So the fractional part, we convert it to what?
Convert it to multiply them by 8.
We multiply it by 8, yes, correct. So let us do this. So yes, so we're going to split n into 139 plus the fraction, which is 0.6875. So each one will be converted separately, and then we are going to join the integer and the fraction later. So let us take here 139 and convert it. So we divide by 8. In the case of the fraction, we multiply by 8. Okay, so this is the procedure. So we take 139 divide by 8, I get 17 point something. But if you multiply 8 by 17, okay, if you multiply 8 by 17, anyone has a calculator? 8 multiplied by 17?
136.
Exactly. So 139 minus 136, you get the remainder, which is 3. Okay. So this is the integer remainder. This is called integer division. So we don't write it as 17 point, we write just 17 as the quotient, and the remainder is 3. Now notice that 3, this is actually is what? It's digit 0, okay, in the integer part. Now we take the quotient, which is 17, and then I divide again by 8. Now 17 divided by 8, we get 2 point something. 16 divided by 8 is 2. But there is a remainder, which is 1. Okay, so 17 minus the 16 will give you the remainder, which is 1. Now 2 now is less than 8. So when you divide 2 by 8, you get 0, and the remainder is the 2. Now this procedure is going to stop. We always stop when the quotient is equal to 0. That's it. So therefore, 139 is 213 in octal. Okay. Now what we have to do is that we have to do the fraction part. So we are going to take the 0.6875 and multiply it by 8. Now when we multiply it by 8, we get 5.5. Now 5 here is my first digit in the fraction. We take the 0.5 and multiply it again by 8, we get 4.0. So 4 is my second digit in the fraction. Now the remaining, so the new fraction now becomes 0.0. So we stop when the new fraction becomes 0.0. If the fraction is not really 0.0, then in this case we have to continue multiplying by 8 until we reach 0.0 or we have sufficient digits in the fraction. So now we can join them. So 139 is 213 in octal. Notice that the 3 here is digit 0. Then we have the 1, then the 2. So it's actually from right to left, whereas the fraction, which is 0.6875, is 0.54. So the 5 here is the first digit that appears after the radix point. Then we have the 4. You can always verify that. You can always check that. All what we have to do now is to join them. So 139.6875 will be 213.54 in octal. Is this clear? So this is an example about how we convert a decimal to octal. Right. If I'm not receiving questions, yes, go ahead.
What's the R in radix stands for?
It means R here is 8.
It's like any number, right?
So when I'm talking about octal, the R is 8. If I'm talking about binary, R is 2. If I'm talking about decimal, R is 10. That's the meaning of R.
Okay.
R is the radix. Okay.
It's the highest number you can use plus 1.
Well, it's actually the digits will be, in the case of radix 8, the digits will be from 0 to 7. We have seen that in a previous slide. If you are using radix R, then you can go from 0 to r minus 1. These are the digits. So when the radix is 2, we go 0 and 1. Decimal, we go from 0 to 9. That's what it means. Okay.
Okay.
So this is the conversion procedure that I just mentioned in the we have seen in the previous slide. So if you have a decimal number n and you would like to convert it to any radix r, we did it actually to binary, so the radix was 2. We did it to octal, so the radix was 8. So what we have to do is that we have to convert the integer part separately, and then we have to convert the fraction part. In order to convert the integer part, we have to divide. We divide n by r, the radix. And if we are converting to binary, we divide by 2. If I'm actually converting to octal, I divide by 8. If I'm actually converting to hexadecimal, I divide by 16. Okay? And then we look at the remainders. And we get the remainders in reverse order. So we obtain digit 0, then digit 1, then digit 2. So basically, we are obtaining them from right to left. This is for the integer part. In the case of the fractional part, we multiply, okay, the fraction by r, by the radix r. So if it is binary, we multiply by 2. If I would like to convert it to binary, I multiply by 2. If I would like to convert it to octal, I multiply by 8, and so on. And then finally, we just join the result. We join the integer part with the fractional part. This is the conversion procedure. It's simple. It's not really that difficult. You just need to practice this. There are many exercises at the end of chapter 1. So go to your textbook and to the chapter and do these exercises and look at their solutions. Okay, they are available in the appendix. Okay. Right. Yes, go ahead. Go ahead.
Where is available?
In your textbook, at the end of the chapter, inside the chapter, there are many examples. You can actually just look at these examples and look at their solution, and then go to the exercises at the end of the chapter. I'm going to actually post many exercises. If you, I'm right now revising the web page for the course. It's available on my website. I'm going to list many exercises for you to practice. So you can actually practice doing these exercises, and you can look at their solution in the textbook in the appendix. Okay. So I'm going to have a link from Blackboard to my to the course web page, and you will find a lot of information. Okay, where you actually can find exercises for you to practice. Is this clear?
Yes, thank you.
Right.
Yes.
So now, sometimes if you would like to convert between binary, octal, and hexadecimal, the procedure can be simplified. Okay, so you don't really have to do what we have seen in the previous slide. So rather than dividing and multiplying, what you can do is that you can start grouping, because binary, octal, and hexadecimal are related. So remember that octal is radix 8, and 8 is 2 to the power 3. So it's related to binary. So I can actually take a group of 3 bits, okay, in binary and convert it to octal. Hexadecimal is radix 16. 16 is 2 to the power 4. It's related to binary. So I take a group of 4 bits and convert it to hexadecimal. So the procedure can be simplified. The conversion procedure can be simplified. So we can start at the radix point. We can convert the integer part starting from the right, and we can move to the left. And then we can convert the fractional part starting from the left and moving to the right. Starting from the first bit after the fraction, after the radix point, and then we can move to the right. Let us take a look at this example. Now notice that this number is in binary, okay? It's a binary number. Notice that this is the binary point. Anything which is to the left of this binary point is the integer part. Everything which appears to the right is the fraction. Clear? Is this clear? Now,
yes.
I'm going to convert this to octal. I'm going to convert this to hexadecimal. So in the case of octal, we look at groups of 3 bits. So we start at the binary point and we go to the left, okay, for the integer part. We start at the binary point and we move to the right in the case of the fraction part. Okay, so for the integer is right to left. So we start here at 0, 1, 1, right? That's actually, this is a group of 3 bits. It will be 3. Next, we have 0, 0, 1. What is 0, 0, 1? It's just 1. Yes. Next, we have 1, 1, 0.
3.
5.
1, 1, 0.
6.
6. Yeah, thank you. 6. 0, 1, 0.
2.
And then 1, 1, 1.
7.
7. Good. Let us do it now for diffraction. In the case of diffraction, I'm going to start at the binary point and move to the right. 0, 1, 0.
1 over 2.
Just just convert it to a digit.
2.
It's just 2. So the diffraction will go from left to right. So 2. Then I have 1, 0, 0.
4.
Okay, good. 1, 1, 1.
5.
7.
And 1, 0, 0, 0. 1, 0, 0.
1.
1, 0, 0.
1.
4.
4.
Yeah, 4. This is 4. And then we have 1, 0, 1.
5.
Now here I have 0, 1.
1.
We can add 0.
1.
Well, 0, 1 is just 2 bits. I need 3 bits. I need 3 bits. So therefore, we have to insert a 0 in the fraction. So whatever actually here is not really shown in binary, you can always insert zeros in the fraction. It does not really change anything in the fraction, right? So in the case of a fraction, you can always insert zeros to the right. In the case of the integer, you can always insert zeros from the left. So for this reason, we need 3 bits. So this is 0, 1, 0. It's not actually 0, 1. It's 0, 1, 0. So what is 0, 1, 0?
2.
Oh, this is 2. It's not a 1.
Yes.
Okay. It's a 2. It's 0, 1, 0. We have to add a third bit here, which is a 0. So this is 0, 1, 0. It's a 2. So you have to be very careful about the fraction when you convert it from binary to octal. Let us repeat. Let us do it actually from binary to hexadecimal. Okay. So what I'm going to do now is I'm going to use here my eraser. I'm going to erase here these shown, okay, the highlighter, and repeat everything and do it in hexadecimal. So how do I convert from binary to hexadecimal?
Take 4 bits.
A group of 4 bits. Yes, group of 4 bits. So let me use my highlighter again. Now, 4 bits, it will be 1, 0, 1, 1. What is 1, 0, 1, 1?
B.
Yes, it's 11. It's B. Then we have 1, 0, 0.
8.
No. 1, 0, 0.
10.
Did you say A?
8. 8.
I said 8. Ah,
Yes,
8. The number 8. Yes.
Yes.
1. Okay, 8. Okay. So how about 0, 1, 0, 1?
5.
Now I only have 3 bits here, 1, 1, 1, but I need actually 1 more bit. So
Add
we
a
can
0 to the left.
we can insert a 0, right?
Yeah.
So what do we get?
7.
7.
Excellent. Start. Now let us do it from the for the fractional part. Okay, this is the fraction. So 0, 1, 0, 1.
5.
5.
Excellent. How about 0, 0, 1, 1?
3.
3.
1, 1, 0, 0.
C.
Again, I cannot hear you.
C.
6.
C, it's 12. C.
Yes,
How
C.
about 1, 0, 1, 0?
A.
Okay, now I'm left with just 1.
3, 0.
We can put right side zeros.
Yes. It will be
B.
what?
8.
8. It will be 8. Yes. Yes. So this is actually how I do the conversion. Is this clear?
Yes.
Yes.
Clear.
Excellent. So now we understand actually how we can convert between binary and octal and binary and hexadecimal. If I would like to convert from octal to hexadecimal directly, I can actually go from octal to binary and then from binary to hexadecimal. And vice versa, if I would like to go from hexadecimal to octal, I can go to binary first and then I can go to octal. Okay? Clear? Is this clear?
Yes, clear.
Could you repeat the last point?
So if I would like to go from octal to hexadecimal, I have to go through binary.
Yes, I get it. Yeah.
Okay, so if the binary is not given, if the octal is given, and I would like to actually to convert to hexadecimal, convert from octal to binary first, and then convert the binary to hexadecimal, and vice versa. If you'd like to go from hexadecimal to octal, go through binary first and then to octal.
Yes, thank you.
Okay, very good. Now let me conclude with some important properties of fraction. I'm running out of time. How many fractional values exist with m fraction bits? If you use m bits in the fraction, how many values? Any answer? Each bit can be 0 or 1. So there are 2 values for each bit, and we have m bits in the fraction. So how many possible fractional values? How many values can you have with m bits?
M over 2?
No, these are just actually bits. So you can
minus m.
so each bit can be 2 values, right? So if you use m bits in the fraction, how many values can you have?
2 power m.
2m.
2 to the power m, yes. But these actually are fractional values, okay? Like in the case of integer, if you use m bits in the integer, you can have 2 to the power m integer values. If you use m bits in the fraction, you will have 2 to the power m fractional
Minus
values. Well, no, we don't. We are just actually counting in total how many fractions we have, okay? We are not saying actually what's the smallest value and the largest value. We are talking in total, okay? So 2 to the power m fractions. Now, here's the question. What is the largest fraction value if you use m bits?
2 to the power m minus 1.
Well, that's not an integer. That's a fraction. So 0.1111 if you use m ones. What's the value of this? Let me give you, let me do it in decimal. If I use 3 digits in decimal, or let us say just 2 digits in decimal, 0.99, what's the value? 0.99. How can you root? So what is the value of 0.99? You can actually, what's the largest fraction if you use it in decimal? 0.99. It's actually 1 minus 0.01. It's actually 1 minus 10 to the power negative 2. So if you write it the largest fraction, okay, value, okay, so you have m bits in binary, it's 0.1111, you have m ones, so it will be 2 to the power minus 1 plus 2 to the power negative 2 plus all the way 2 to the power minus m. Now the value of this number, okay, this is a fraction, okay, it's less than 1. It is 1 minus 2 to the power 2 to the power negative m. Because if you add 2 to the power negative m to this number, you will get exactly 1. Okay, so it's slightly less than 1. It's like 0.9999, so many nines in decimal. So if you add 2 to the power negative m to the number, you get exactly 1. So let me say in general, okay, the largest, okay, fraction value, if you use m fraction digits in radix r, it will be 1 minus r to the power negative m. Because if you add r to the power negative m to this value, so it's r to the power negative 1 plus r to the power negative 2 and so on. Plus r to the power negative m, so it will be 1 minus r to the power minus m. It's slightly less than 1, okay? It's very close to 1, but not exactly equal to 1. So for example, if you use it for decimal, it will be 1 minus 10 to the power negative m. If you use it in binary, it's 1 minus 2 to the power negative m. If you use it in hexadecimal, it will be 1 minus 16 to the power minus m. I'm running out of time, so that's it for today. Let me actually pause here. Okay, so let me just stop the recording. Okay, very good. Type. So today's lecture will be about binary codes. Last time I talked about fractions, how we can represent fractions in binary. We have seen also how we can convert actually fractions. We can convert them actually between different number systems, between binary, decimal, octal, and hexadecimal. But we can also use other number systems if you want. We can change the base or the radix. Today, I would like to talk about a new topic, which is about binary codes. Okay, so we have seen numbers, okay, how we can represent numbers in different number systems. But how about things like characters, colors? How do we represent them? The way to do this, remember that the computer system is a digital system. So we have to represent everything as digits, as numbers. So in order to represent characters and colors, we have to represent them with numbers, okay, with digits. So we define the set of all the elements that should be represented, and we assign a unique binary code to each element of the set. So it depends on how many elements I would like to represent, and we have to decide on the number of bits. Since everything is represented in binary, we have to decide that how many bits in binary we need for these elements that we have in this set. So if we have n bits, we can represent 2 to the power n values, okay, with, let me use here my highlighter. So if we use n bits, okay, in binary, then we can have 2 to the power n, the number of values, okay, that we can represent in binary. And if each element in the set is represented uniquely with a binary number, we can represent 2 to the power n values or elements in the set. So, so this is called coding, okay? So we can assign a code to each element in the set. So for example, if we are dealing with characters, we can assign to each character, we can assign it a code. If we are dealing with, let us say, colors, we can assign to each color, we can assign to it a code. So this is how we can deal with non-numeric data. We can also do coding for decimal numbers, for decimal digits. We can also use the same idea, the same technique to represent decimal digits. I will also talk about this. Let me start first with non-numeric data. Okay, so suppose I would like to represent colors. If I would like to represent colors, let us say I would like to represent them with codes. Suppose I would like to deal with the colors of the rainbow. So there are 7 colors of the rainbow. So the question, how many bits do we need to represent the 7 colors of the rainbow? So we need 7 values, okay? So 7 codes. So how many bits do I need to represent 7 codes? This is the question. Now, if I use 2 bits, how many values we can have with 2 bits? If we use 2 bits, how many values can we have? 4. This is the question to you. 4. 2 to the power 2 is equal to 4, exactly. If I use 4 bits, how many values can I have in binary if I use 4 bits?
16.
16, exactly, 16. Now, 16 probably might be too much, okay? 4 bits, we don't need 4 bits to code the 7 colors. If we use 3 bits, how many values can we have with 3 bits?
8.
8, exactly. So 8 might be reasonable, okay? So we need more than 7. Well, at least 7, at least we need 7 unique values. So if I use 8, okay, that will be good because I can actually have a unique value, a unique code, okay, for each one of these 7 colors. If I use 4 bits, I will have 16, okay, but that will be too many. If I use, let us say, 2 bits, I will only have 4 possible codes, but this is not sufficient. So the number of bits which are needed, or the minimum number of bits which are needed to define 7 unique values will be equal to 3 bits. So 3 bits will define 8 possible values, but only we need 7. So for example, we assign red, okay, we can assign it uniquely the code 000. Orange, for example, can be 001. And finally, let us say violet will be 110. So these are the 7 colors of the rainbow. So 3 bits, as a minimum, we need 3 bits. If I use 4 bits, I can have up to 16 codes, but I don't really need 16. Now notice that I'm defining here okay, only 7 codes, okay, for these 7 colors. There is actually 1 code which is unused, because 3 bits will define 8 codes. 1 of them will be unused. Notice that the code 111 is not defined. It's not used. Okay, that's fine. We can actually sometimes have, okay, extra codes that are not really used, not because we don't really have, we only have 7 elements in this case. We don't really have 8, but that's fine. So as a minimum, we need 3 bits, but 3 bits can define 8 codes, but we only need 7. So therefore, there is 1 code which is unused. Okay, is this clear? This is really the idea of coding. You assign a unique code to each element in this set. So here my set is a set of colors, and we have here 7 colors. So we need a 3-bit code. Okay, this is how we determine the number of bits for the code. If we had more than 8, let us say more than 8 colors, then I need more than 3 bits. Now, I could have done a different assignment. I could have started with red as 001 and violet as 111. This will mean that 000 will be unused. You could actually have a different assignment for these different colors. So this assignment is not unique. You can change it if you want. You can start at 1 and you can end at 7. 111 will be 7. And 000 can be unused. For example, we can use 000 to indicate black, for example. When you have the lack of any color, we can use it as 000. So we can actually come up with a different assignment. So this is just an example of an assignment where we assign to each color a 3-bit code. Okay, so this is called coding. If you have any question, interrupt me. Otherwise, I'm going to assume that you understand the topic. I'm going to move faster, okay, fast to the next slide, and so on. So the minimum number of bits, okay, the minimum number of bits which is required to encode, let us say, a set of elements. So here my set consists of M. M is the number of elements that I have in this set. So because we are going to represent each element with a binary code, so binary here, it means that the base is 2 or the radix is 2. We have to determine N. N here is defined such that M will be between 2 to the power n minus 1 and 2 to the power n. Notice that M is greater than 2 to the power n minus 1. So n minus 1 bits are not sufficient. And it is less than or equal to 2 to the power n. So that's how we define n. It must satisfy this inequality. Now, you can take here a look at n. You can calculate n as log base 2 of m, but you take the ceiling function. So here, when you put, so x here, this is the meaning of the ceiling function. Okay, so the ceiling function, it's the integer which is greater than or equal to x. So if log base 2 of m is not an integer, you have to look at the nearest integer, which is greater than or equal to x. Right, let me ask you this question. If I have 10 decimal digits and I would like to assign to them a binary code, okay, so let us do the encoding for digits, for the 10 decimal digits. How many bits do I need to represent 10 decimal digits in binary?
4.
4, yes. I cannot do it with 3 because 2 to the power 3 will be 8 digits, but I have 10. So therefore, I have to go to 4 bits. With 4 bits, I can represent 16 elements, but I only have here 10 digits. So I can represent with 4 bits, I can represent 16 digits, but in decimal, we only have 10. So therefore, we have to go with 4 bits, but there will be actually 6 digits, we have 6 codes, okay, binary codes that will be unused. So the answer here will be log base 2 of n. Log base 2 of 10, okay, is 3 point something. It's greater than 3, but less than 4. So we take the ceiling function, and therefore it becomes 4 bits. So we use 4 bits to represent 10 decimal digits. Okay? So this is called coding. Now, in the past, okay, in the early days of computing, when people have invented computers, okay, they used binary because, as I said, that it's actually is a lot easier to design digital circuits that will use binary numbers, ones and zeros. For example, using high voltage and low voltage. Okay, I talked about this in my introduction. Okay, last week. So they faced the problem, how do we represent 10 decimal digits? So they decided to assign 4 bits to each decimal digit. So they invented decimal codes. So decimal codes, okay, so as we have seen that binary numbers is the most natural for computers, but people are used to the decimal number system. So therefore, people came up with the idea, why not to use binary to assign codes in binary to these decimal digits. These are called decimal codes. So we need actually 4-bit codes because a 3-bit will not be sufficient. We have 10 decimal digits, so therefore we need 4 bits. Okay, so with 4 bits, we can actually have 16 unique codes, combinations. Okay, of 4 bits, we can actually start from 0, 0, 0, 0 to 1, 1, 1, 1. Okay, so these are 16 unique values, but I only need 10 digits. So therefore, there will be 6 codes that will be unused. So 10 codes will be used for the 10 decimal digits, and 6 will be unused. Okay. Now, how do we assign the code to each digit? We can actually come up with different ways of doing it. For example, BCD. BCD means binary coded decimal. So we assign here to the decimal digit 0. We start at 0, 0, 0, 0, and we go all the way to 9, which is 1, 0, 0, 1. Now notice that this number in binary will be 9 in decimal. So basically, we assign to each decimal digit, we assign to it a unique, okay, BCD code, binary code. Okay. Now we only have 10 digits, so there are 6 codes that will be unused, which are from 1010 to 1111. These are unused because we only have 10 decimal digits, and with 4 bits in binary, you can have 16 codes. So therefore, 16 minus 10 will be 6. So these 6 codes are unused. Now, we say that BCD is a weighted code. Now, notice that each bit has a weight. The most significant bit has a weight of 4, is a weight of 8, then 4, 2, 1. Okay, so when you look here at 1001, okay, the most significant one will be 8. This is 0. This is 0 plus 1. So 8 plus 1 will be 9. So we call it a weighted code. Okay, let us take a look at 7. 7 will be 0, 1. This one is 4 plus 2 plus 1 is equal to 7. Okay, so the code is weighted, and the weights are 8, 4, 2, 1. So each bit has a weight. Okay, the least significant bit has a weight of 1. The most significant bit has a weight of 8 because we have only 4 bits. So we call it a weighted code. And there are 6 codes, okay, which are invalid. These are not really valid decimal digits. These are 1010 to 1111. Now, if you have the number 13 in decimal, then you can represent it with 2 BCD digits. So the 1 will be 0001, and the 3 will be 0011. Notice that this is the BCD representation. So each digit in decimal will be represented with 4 bits with a code, okay, with a BCD code. And the BCD code will consist of 4 bits. So if you have 2 digits in decimal, you have to represent them with 8 bits in BCD. Is this clear? This is the meaning of BCD. This is actually binary coded decimal. So we are using coding for the decimal digits. Now notice that this is different from conversion. Okay, so conversion is when we convert decimal to binary is different from coding. For example, when I have 13 in decimal, okay, we can convert it to binary as 1101. This is called conversion. So you can represent the entire number 13 in binary. Whereas coding, you take each digit in decimal and you code it in binary. So you code the 1 separately as 4 bits, 0001, and the 3 you can actually code it as 0011. So this is called BCD coding, okay? So you have to understand the difference between coding and conversion. Conversion, you look at the decimal number as just one number and you convert it to binary, whereas in coding, you extract each digit, each decimal digit, and you code it in binary. So in the case of conversion, we got only 4 bits. In the case of coding, we got, for each digit, we got 4 bits, so we got 8 bits in total. So the number of if you have n decimal digits, if the number has n decimal digits, okay, and you would like to code it, then you need 4 times n, the number of bits in BCD. Whereas if you would like to convert it to decimal, you might actually get much less the number of bits. Okay. So there is a difference between converting the decimal number to binary and between coding it in BCD. Any question about this?
Doctor, can you back to slide 41, please?
Can I go backwards? Okay, this slide.
Yes, the weights are 842.
8421. Yes. So the most significant bit has a weight of 4, and the least significant bit has a weight of 1. It's just like, okay, converting it from decimal to binary, but we take it digit by digit. So for each decimal digit, we can represent it in BCD.
Yes.
Okay. Now, BCD is not the only code. We could actually have done different assignments. So BCD is just one assignment, one way to code the decimal digits in binary. There are other ways that people have invented. So BCD will start from 0000 and it will end at 1001. And the remaining six codes are unused because we only have 10 decimal digits. So people have thought that, okay, maybe if we have different codes, okay, if we use different weights, we might actually end up with different codes. So they came up with different ways to code the decimal digits from 0 to 9. For example, if we use 5421, now we give here, rather than giving 8 as the most significant bit, we give it 5. This is also a weighted code, but the most significant bit is 5. Now, when we have the number 5, okay, the first thing you have to do is that to assign 1 to the most significant bit. Although we could actually have encoded 5 differently as 101 here, like in BCD. In the case of the 5421 is not the 8421 BCD. So therefore, we start always with 1. So if the number is 5 to 9, we always assign 1 to the most significant bit, okay? Because the most significant bit has a weight of 5. So therefore, we start with 1 with the most significant bit, and then 6 becomes 1001. So this will be 5 plus 1, 7 will be 5 plus 2, 8 will be 5 plus 3, and 9 will be 5 plus 4. Okay, so this is a different way to assign the code to these decimal digits. So it's called 5421 code. This is just a third possibility is to use 2421. This is yet another way to assign the code, okay, to these 10 decimal digits. So notice that from 0 to 4, the first 5 decimal digits from 0 to 4 are identical, okay, in BCD 5421 and 2421. The difference is that when you reach 5, So when you reach 5, 5 is encoded as 1011. Now that's interesting because 1011, if you look at the weights, this will be 2 plus 2 plus 1. Okay. Again, we did not choose 101 because 101 will give you also 5, but they assigned a different code. So 2421 will uniquely assign 51001011. So this 1 is 2 plus 2 plus 1 will give you the 5. If you would like to get 6, it will be 1100. So this is 2 plus 4 will give me the 6. And finally 9 will be 1111, which is 2 plus 4 plus 2 plus 1 will give you the 9. So therefore the weights are chosen so that their sum is equal to 9. Now that's an interesting code, okay, an interesting weighted code. Okay, now notice that, okay, it's a 2421 is self-complementary. In other words, if you look here at 4 and 5, 5 is the complement of 4. So you have 0, 1, 0, 0. Now, if you complement the bits, the 0 becomes the 1 and the 1 becomes a 0. You can see that 5 is the complement of 4. You just have to change the 0 to a 1 and change the 1 to a 0. Now, notice that 6 is the complement of 3. 3 is 0, 0, 1, 1. 6 is 1, 1, 0, 0. And finally, 9 is the complement of 0. So this is 0, 0, 0, 0, and this is 1, 1, 1, 1. So it's chosen in a clever way. The weights are chosen so that 5, 6, 7, 8, 9 are the complements of the digits above them. 5 is the complement of 4, 6 is the complement of 3, and finally 9 is the complement of 0. Okay? So basically just have to complement the bits. There is also another weighted code, which is 84, -2, -1. In fact, you can choose the weights to be negative. Now, in the 2421, 5421, and BCD, all the weights are positive. But there is no reason why not actually making it negative. So if you choose a negative weight, okay, suppose I would like to have, let us say 1. Now, 1 will be represented as 4 minus 2 minus 1. So this will be 1. Whereas 2 will be 4 minus 2, and 3 will be 4 minus 1. And then you have 4, which is 0, 1, 0, 0. And then 5 will be 8 minus 2 minus 1, and so on. Notice that the 8, 4, -2, -1 is also self-complementary. Look at the bits, okay, the codes here for 5 and for 4. So if you complement 0, 1, 0, 0, you will get 1, 0, 1, 1. So notice that 5 is the complement of 4. And 6 is the complement of 3. And all the way here to 9, which is the complement of 0. One last coding system, or one last example, is the excess3 code. Okay, this is a different coding, okay, for the decimal digits. Notice that we take every decimal digit, we add to it plus 3. This is why it's called excess3. So we add plus 3 to the decimal digit. So 0 becomes 3, and we encode it in binary 0, 0, 1, 1. 1 becomes 4, so we encode it as 4. And finally, 9 plus 3 is 12, so we encode it as 1, 1, 0, 0 in binary. Now, excess3 is also self-complementary. Notice that 5 is just the complement of 4. So 4 now is 0, 1, 1, 1, and 5 is 1, 0, 0, 0. Okay, it is also self-complementary, but it's not weighted. It's not weighted. So unlike the first 4, they are weighted. Excess3 does not use weights. It just adds 3 to the digit. So 5 plus 3 is 8. It will be encoded as 1, 0, 0, 0. 4 plus 3 is equal to 7. It will be encoded as 7 in binary. Is this clear? So these are codes, decimal codes, that we can assign to the 10 decimal digits, and we have seen that there is more than one way to code the 10 decimal digits.
دكتور
تفضل.
How the computer know how to distinguish between these codes, between these systems?
It's the software. Okay, it's not the hardware. It's the software. Okay, so for example, if you are using BCD in your program to represent the decimal digits, you as a software designer, you can actually tell, okay, the meaning of these bits. Or you can design a special circuit in the hardware that uses a special code. So for example, if you don't really want to do conversion, okay, sometimes circuit designers use a certain code to represent these 10 decimal digits. So you as a designer of this circuit, or if you are using software, you are writing the software, you can decide, okay, whether you would like to do, let us say, conversion, or you would like to use coding, and you give a meaning to the bits. So remember that the bits have no meaning. When you store bits inside the memory of a computer system, they have no meaning. Okay, it is us as a human beings or the software who is actually assigning. So if you're just storing bits, okay, you cannot tell what these bits actually mean. They can mean anything. Okay, so we use bits to represent integers. We use bits to represent fractions. We use bits to represent negative numbers. I'll talk about negative numbers later. We use bits to represent, let us say, characters, colors, and so on. So the software gives a meaning to these bits. Okay, I'm just giving you an idea here that how you can code, okay, the decimal digits in binary. Now, how you would like to use these codes, it's up to you. You can design a special circuit that will do the coding of the decimal digits. If you would like to avoid using binary, you would like to do, if you would like to, to avoid doing conversion to binary, you can actually use BCD codes. You can use codes. And there are different ways to assign the codes to these 10 decimal digits. Okay. One more example, which are the character codes. Okay, so what we have seen in the previous slides, okay, are codes which are assigned to the 10 decimal digits. How about characters? Okay, characters are not really are symbols. Okay, and okay, we need to assign codes, okay, for these characters. Not only that, but we have to standardize the use of these codes because the same characters have to be represented exactly the same way across all computers. Because let's suppose that you have a document on the internet and you download it on one computer system or another computer system, okay, the codes have to be represented exactly the same way on all computers. So there must be a standard. So people have invented standards for characters. For example, the ASCII. ASCII is a standard. It's the American Standard Code for Information Interchange. This is how they interchange text across different computer systems. So if you take, let us say, a text file and you store it in it characters and you would like to open it on another computer system, you should be able to read exactly the same characters. So they assign 7 bits, okay, to each character. So the original ASCII standard used 7-bit character codes, and these are numbered from 0 to 127, because with 7 bits, you can have 128 possible values in binary, and you can number them from 0 to 127. But then people have extended, okay, the ASCII to become 8 bits. So now we have 8-bit character codes, okay, so with 8 bits, you can have 256 possible characters. So we start at 0, we end at 255. But then 256 is not really sufficient to represent, let us say, all the characters of all languages around the world. Okay, so for example, to deal with the Chinese, Japanese, and Korean, you have more than 256 characters. Okay, so these people have languages that have a large number of characters. In English, there are only 26 characters. You can actually have 26, 26 letters. You can actually have 26 lowercase letters and 26 uppercase. And also you have some kind of special characters. Okay, let us say for a comma, for a period, semicolon, for parentheses, brackets, braces, curly braces, and so on. And the different operators like, let us say, addition, plus, minus, multiply, divide, and so on, slashes. So you have actually all sorts of symbols that you would like to assign to them codes. But then when you deal actually with Chinese and Korean and so on, they have more. So you cannot really fit it actually within an 8-bit character set. Okay, so 8 bits can only represent 256. You need 16 bits. If you use 16 bits, so the Unicode standard was introduced so that they unify the representation of characters, okay, around the world. Okay, so for all different characters, okay, it includes English, Latin, different characters, Chinese, Japanese, Arabic, and so on. Okay, so all of these characters are represented in Unicode, and they assign a unique code to each character. So it's called a universal character set. Okay, let me show you here the original, okay, 7-bit ASCII codes. These are called printable ASCII codes. Okay, so space itself is a character, and it is shown here in hexadecimal. So notice that the columns here are numbered from 0 to F, where F here is 15, A is 10, B is 11, and so on. And we start here at 2 to 7. So if you would like to find the character code, okay, or the ASCII code for a given character, for example, 20 in hexadecimal will be space. If you converted 20 from hexadecimal to decimal, it will be 32 in decimal. 21 will be the exclamation mark, and so on. So we have different symbols. Okay, okay, all of these are called characters, and each one is assigned a unique code. So if you would like to find, for example, what is the code, okay, for the character A, for capital A, it is 41 in hexadecimal. So look at the row and the column here, okay, and join them. So 41 in hexadecimal, it will be 65 in decimal, and this will be a unique code for the character for capital A. For lowercase a, it is 61 in hexadecimal. Okay, so this was the initial ASCII code character set, and it is a standard. Okay, so all computer systems will follow the same standard, and this way you can interchange text files having these characters. But this was extended to 8 bits, and then it was extended to 16 bits to include actually many other characters, okay, including Arabic, different European languages, Russian, okay, as I said, Chinese, Japanese, and so on, Korean. All of these were added in the Unicode character set. Okay, is this clear? So whenever we are dealing with, let us say, symbols, okay, so this is a character set, and we have to assign to each character a code. So the code is a binary number which is stored inside the memory of a computer or inside a file. So basically the characters become digits, become numbers, become codes. Okay, questions? Right, I'm done with this topic. Okay, I did not show you the control characters. So here row 0 and row 1 were not really shown. Each row can have 16 characters, okay, because we have 16 columns. I did not show you row 0 and row 1. These are the first 2 rows are reserved for control characters. So control characters are not really printable characters. You cannot actually print them on the screen. What they do is that they have special meaning. For example, character 0 is the null character. Okay, people use it in some programming languages, like in the C programming language, C, C++, and other programming languages. They terminate the string with a null character. So every string must be terminated with a null character. So it marks the end of the string. For example, character 9 will be the horizontal tab. Okay, you have a tab key on your keyboard, and it is represented by character 9. Okay, for example, character 0A in hexadecimal or 10 in decimal is the line feed. 0D, which is 13 in decimal, is the carriage return. So these these control characters can control the movement of the cursor, okay? Or they can actually mark the end of a line in a text file. So these are control characters, okay? Because you can actually use these characters, okay, to control the movement of the cursor, or you can use them, okay, to mark the end, let us say, of a line in a text file. So every line must be terminated with a line feed, and sometimes they use line feed and carriage return. So two control characters to mark the end of each line. Anyways, these are called control characters. They are not really printed. You don't really see them, okay, in a file, but they are stored inside the file, okay? Right. So that's it about this presentation, okay? There is more here topic about parity and error detection codes. I'll come back to this topic later, okay, about parity generation and parity error detection, okay, but I'll skip it for now. There are only 2 slides here, so I'm going to skip it for now, and then I'll come back to it in a later presentation.